So before I start, I'd like to take this opportunity to thank the CSPP team. This is going to be my first ever talk in the 15 years that I've been associated with the team, so it's quite exciting for me. What I'll talk about is a bit of the background that we've had with Amazon, and the reason for that is that my PhD is actually in business, and they have a theory that says the things that a firm does all are based on what they call its path dependency. So basically what happened to it. And a great example of this is Apple, the iPod company. So Apple computing. And if you remember, if you're old enough, in the 80s, Apple almost went bankrupt. Their stock price was down just under $2, and they were in dire straits of going bankrupt. And Microsoft bailed them out and saved them. And the definition of bankruptcy is you can't pay your bills. So ever since then, Steve Jobs maintained a massive war chest of funds. And the longer the company went on, the bigger it got. When he finally exited Apple, their war chest was in the billions. And a lot of it was driven by his experience in the 80s with that almost bankruptcy. So how we got to the system I'm going to tell you about today is based a lot on our experience with Amazon starting, I think, in 2018. And so what I'm going to talk about is that piece that Lewis had in his architecture diagram. And Alan mentioned what it actually is in his speech yesterday. It's a processing engine. And what it does is it strings together all of the different pieces of the CSPP algorithm. So that's what I'll end up talking about if I can get this thing going. No, left button. Okay, so what we have here is the first and most obvious question is why would you build a cloud-based system? Why would you engage Amazon services of anybody for that matter? And the reason is, like Lewis mentioned, that the upfront costs are lower. You don't have to build an entire antenna system. And I've got a list of the ground station providers down on that right side. And while it's up there, I'll take this time to satisfy NASA's legal counsel and say that we do not endorse any of the products on that list. And that held up my presentation for a whole day, so it was a lot of stress. So that's a brief list. And what I've done is I've plotted the station locations. This should be pretty current. I grabbed the list a few days ago. And so you can see that there are gaps in coverage. There was a question about coverage. And so like we were talking about, if you'd like to see the more western parts of Africa, it's not possible with Amazon because there's no antenna. And so that's also why we're looking at using other providers as well to kind of enhance the coverage that we can offer to people. Perception. And so the second reason why you'd want to do this is you can receive the broadcast whenever you want to get it. You don't have to plan in advance. Although if you're talking about like a Veers reception, which is all we do, there's only a few passes per day. There's only 2. And with the ground station, you might only get 2 or at most 3 viable chances to get the information in each overpass. I mean, in each half of the day. So at most, you'll ever get 6 overpass opportunities, depending on how close the satellite is to the ground station. So that would be why you'd want to do it. And really, you can scale with Amazon, and that's one of the big advantages. And there was a brief bit of talk about that, where you can get processing capability on demand. And we really do that. Looking at Russ's chart, he mentioned he had a 6 CPU system. We actually use an 18 core because we found that if we use a lot of cores, we can run most of CSPP in parallel. And so that's what I'll talk about later in the engine itself. And so this is how the initial implementation works. And you'll notice this diagram is very similar to the diagram we saw earlier from Russ. And what we call this is and I've had to redraw it for copyright purposes. What we call this is the version 1 from Amazon. When we started with the service in, I think, 2018 or 2019, this was the recommended architecture to use. And Russ's diagram still kind of looked like this, from a NASA standpoint or from a government standpoint, this is a troubling way to do it. And the reason for that is that when it initially came out, you would have that leftmost blue block, the origin region. You would have your processing capabilities, in particular RTS, TPS, and some of the radio handling, that would need to be located where the antenna was. And it's not a big deal. There's 10 stations, but if you're in the government, every week you get a security patch, and you've got to go and patch the instance and update it. And so that if there's 10 ground stations, you have to patch 10 stations a week. And so it becomes a management issue to have this structure. But what is key and what going forward is you'll notice the structure has that S3 bucket in the middle that Russ talked about. And S3 is a global resource. And so that really is the key to unlocking low maintenance for your systems, is to drop things off in the S3. And so actually I think that should be, no, that's correct, that's Virginia region. So we do process in the Virginia US East 1 region. I'm sorry, we process in Ohio. I wish we did not process in Virginia. That's actually one of the least reliable regions that Amazon has. I think it actually is the least reliable. And that's not a bad, I'm not dogging them. They're down 1 or 2 days a year, and it's getting better. And it's just because of the age. That's one of the older regions. And so that'll lead me into a little bit of architectural talk later. So continuing on with this management problem, you can see after you expand a little bit, you end up with that structure on the right. So you can see there's one processing blob that takes your data from the S3, and that's at the bottom. But like I was mentioning, you have all of these EC2 instances that are, they don't have to be running, but they're deployed at all of the antennas. And that is a lot of work. And the reason I know that is because I have to do it. So you don't want to really kind of have that too much. You'll also notice I can barely see it. Inside of there are the processing components. In the earlier days, you would need Data Defender to process the radio stream as it came in. And you'd also have some custom code from Amazon that would remove the Vita49 packaging around the stream. And then you could put that into RTS TPS to produce your output. And so I've shown here that this is the US East region. There's actually quite a number of data centers. It's pretty tricky to get the actual address of the data centers. Maybe Russ and I will have a talk about that later. Okay. And so this is our processing flow in this version 1 setup. And what we initially had and what Amazon was initially recommending was using IPOP. And so in the initial version 1 setup, after RTSTPS ran, it would invoke and install an IPOP instance in EC2. And the problem with IPOP is it's not really designed to operate in a one-off environment. IPOP is designed to run 24/7. It receives data, it tracks the data. And for us, when we were developing, that was a big problem because we would process a test satellite overpass, and if you pass it to IPOP again, IPOP says, I already saw that, I'm not going to do it. And so it produced some really troublesome issues when we're developing. Just because of the size, there's MySQL database that's distributed with IPOP as well. And so about this time, we started looking more at what we could do with STPS, IPOP, and we started to become aware of CSPP. And what you end up having is a structure here, and it seems innocuous enough, but the real problem here is it's a single processing chain, like a script, if you will. And so you would run RTSTPS, and then you would run the CSPP, SDR, and then after that, if you wanted floods, you would run that, and you would run fire. And if you want to accommodate the different satellites, they have different naming conventions for their files, and so you end up with, in this case, there's 4 separate scripts that we would maintain. And I think this is the way everybody does it, because when you get the CSPP documentation, it tells you how to run it. And so you start stringing those together, and then, well, I'm going to do another satellite. And so you string another set of scripts together. And after a while, you get a lot of scripts, especially if you're producing different products. So this is our first iteration at it using the original 2019 Amazon stuff. And then this is the magic I spelled it wrong. After talking to Russ, it's not CRDD, it's XRDD, stands for Cross-Region Data Delivery, like he was saying. And this is a massive, massive change. It's hard to underestimate how important XRDD is. And what you get is a change from that architectural diagram I showed you earlier where you've got 10 instances, one at every antenna. And what you have now is you have the antennas, and the antennas magically do all of the work of the initial processing that's done in those works in the radio file. And what you get is a file dumped off in S3. And as Russ was mentioning, it's every 30 seconds, which is awesome, and we'll talk about that later. That's a future improvement for our software. But it's dropped off in S3, and then you can process wherever you want. And the Lambda triggers aside, the Lambda triggers are great. We use them a ton. But the key is the CRDD, the XRDD, because you can now process and decouple the processing, and you don't have to manage and maintain all of those instances. So you just have one to work with. And in our case, I'm going to take a slight diversion, and when you look at this diagram, it's the product of what they call a cloud formation. And if you start to use AWS, everybody starts the same way, I suspect. You just go to aws.com, the website, and you start clicking around, and I need an EC2 instance, and you'll create it on the web page, and I need security rules, and create those on the web page. What the CloudFormation template does is it allows you to automate the entire process. And it doesn't become important until you get big. It's a scale issue. And so we have a number of systems running in AWS. And without CloudFormation, it could be very challenging because when you go to look at the Lambda functions page and there's 100 of them and you don't know what they do, you don't know if you can delete them. Or if you're using EC2 and you just start an instance using EC2, using the console, if you're not careful and you say, go ahead and make me a security group, it'll do that, but it doesn't clean it up after. And so you're looking at your security groups and there's 200 or 300 of them. Where can I delete them? Don't know. Could be bad, right? Because you have multiple applications running at the same time, and it could be someone else's application. I suspect that is why a lot of companies are having trouble pulling out of USEs to deploy in other data centers, because it's really hard to figure out, like, who owns this thing? There's tagging, but who tags? Who leaves a little message about who owns it? I mean, we try and do that a lot. It's really important, but it's hard to do that. And what CloudFormation templates do is they allow you to abstract the whole thing. And when there's security requests, which is our new model is, we get a request from security and says you have to update. We just go to the CloudFormation template page, turn the formation off, and turn it back on. And when it comes back up, it automatically reloads the newest versions of the operating system, so it's security compliant. So can't say enough about CloudFormation templates. They're awesome. Once you start to use them, there's a lot of bits that are at the edges in terms of documentation. It can be very challenging to implement towards the end because, 5 minutes, oh my God. What you have is S3 is a global resource, and the IAM, which is the security aspects, are also global resources. So if you make a CloudFormation template, and that template is deployed in US East, and then you take it and you deploy it in Oregon, you'll run into problems. And the reason is because you have global resources defined inside of your regional template. So you have to separate the templates, and you have to do it carefully so that they overload, they don't overlap. You can't reuse. You can reuse security pieces or authorizations, but it's not a good idea because if you have more than one application and you shut one down, you can't shut it down until you shut the other one down. So there's dependencies. So you have to be very careful about your use of the global resources. But that said, it still doesn't take away from how awesome CloudFormation is. You can also see that we have containers. We've containerized CSPP. The 34 gigabytes that I think Liam was talking about, that is a common size. I think ours, when we started, was 42 because we have RTSTP now inside of our template as well. The key to getting out of that, because we use Amazon Batch, and the reason for that is we only want to pay for when we're processing. And Amazon Batch also allows us to scale. So if we add new applications, we just say, oh, I need another 30 CPUs. So I just change the type in my CloudFormation template, and now I automatically will get that the next time it runs. And so batch is great because of the pricing. It can be very tricky. Again, batch in CloudFormation is the very edges of the documentation. We've run into a lot of struggles. I think Russ was talking about it today when he was saying EFS is the way to go. And we've implemented EFS. It's at the very edge of documentation. And the reason is that if you look for documentation on how to attach EFS into these systems, it's all written for the older Amazon systems. They call it Linux 1, and we use Linux 2. So that you have to kind of finagle around and try and find an augmentation for the documentation. So that's our work in progress. And so we decided, after working with IPOP for so long, that we're going to switch to CSPP. It was just too much. What you see here is the IPOP screen. I'm not sure how familiar people are with IPOP. And this is how IPOP functions. And when it's running, it has a VNC server, so you can log into it and see what it's doing. And so what it's doing up there is doing actual processing. And the important thing that we took from this is it shows you the steps in the processing. So L0 needs to come before L1, L1 needs to come before L2, and more importantly, those steps need to be successful. Right? You can't get L2 if you have no L1. And so we use this as our template, and we came up with this idea that we're going to abstract out CSPP and treat it as a step. And I'm going to go into steps in a little bit more on the next slide. And this is where things get confused, so I'm going to try to talk a little slower and try not to confuse myself. So we came up with this idea of the steps, which is basically RTS TPS is a step. The SDR is a step. And each step, we're going to give a name so that we can refer to it. And in addition, it's going to have a requirement. And the requirements of the step, and this is very similar to yesterday's talk about the XML in the delivery of the algorithms. So we use a similar system where each step, say I'm going to run CSPP SDR. It's a prerequisite for that step that RTS TPS not only completed, but completed successfully. And so we conceptualize this as, well, okay, we have to complete all these steps and there's prerequisites. And when things are done, we need to have a way of letting everyone else, all the other pieces in this ecosystem know. And so that's where the name comes in. The name is how we tell the other algorithms that we're done. And so what the engine is a giant bag of names. And the names grow over time with a start tag, an end tag. So if RTS TPS is the step, there's going to be an RTS STPS start tag generated when it starts, and when it ends, the engine will generate an end tag. So it's just really tracking these bags of names. And what that allows parallelization and initialization. Parallelization is the key, and it's close to running out of time, which is surprising. And so this is the actual execution of the engine, like a flow. You can see that RTS TPS is the blue block, that's the step we're doing, and the orange are all of the different state tags that are generated from each step. So the blue is a step, and those are the tags that are generated. And you notice that the way that we've got these processing times is we must run RTS TPS first. But then after that, we run all of the algorithms, so the VIRs, CRIS, and ATMS are all run simultaneously, which is why we use a bigger instance than what we were talking about earlier. We use all 36 cores or 26 cores. We use a lot of cores because all those algorithms are running simultaneously and in parallel. And then on success, the follow-on routines are also run. And I've only traced from level 1, you can see we did the VIRS flood, fire, and the true color, the polar to grid. Those steps are also run in parallel for each piece. And steps are not only just the processing, we transfer to S3 as a step. So S3 transfers weight for the VIRS true color success, and then it will transfer out the files. Then that will start the next step. So it's really just a state-driven engine. It's not that complicated, but it results in a lot of benefits. The first is parallelism. We have tremendous speed gains. From what we can tell, we're doing pretty good in terms of the speed. There's not a group that we're aware of right now that can produce higher speeds, and it's because of the massive parallelization, the ability to throw Amazon hardware at the problem. Modularity and flexibility are important because over time, as things got more complicated, having all of this modularity makes it easier to make the system more advanced. Finally, the complexity. Our scripts, those scripts that we talked about, the 4 scripts to handle, the different satellites and instruments were very complicated because we did error checking. Right? You can't do level 2 unless level 1 is successful, so you have to know. And so with this engine, we've reduced our code size by 70% just by removing all the error checking. Now it just happens in one little routine. And so that's also results in simple debugging, right? There's less code to debug. Let's see. Oh, yeah, okay. I guess, yeah, I'll mention the last point. So the metadata. We've recently been focusing on mostly trying to process metadata. And so all of the CSPP commands are all stored as metadata. They're not actually hard-coded into the engine. So the engine just loads up these scripts of metadata and then runs them for all of the different satellites and instruments. Okay, so going forward, what we'd like to do is additional input sources. You heard mentioned about that, Azure and the other direct broadcast receivers. For us, it's merely changing out the front end piece. So we just change metadata. But we'd like to add those, and it takes forever to onboard anybody, actually, just for the testing and everything. Increases in capability, we'd like to add more options. Right now, what the engine will do is to support external parties. You can have tag steps that are based on completion, and those can be web requests. So the system will call out to other systems, or it'll call Lambda functions. So if you're not part of the system but want to be, you can say when level 1 is done, send me a web request, and then I'll go pick up the S3 files as part of your response. So it's designed to integrate other people's things into it. So at any step, you can join into the processing chain. Going forward, we'd like to parallelize and take that to the next level. And so what that means is when you get an overpass, you'll have multiple granules inside of the overpass. In, say, a 15-minute overpass, you'll get 5 or 6 granules. We'd like to process those. And I have a quick diagram about that. We'll look at that after we talk about this. So MQTT, the Rabbit MQ system, that is great. We use that for monitoring. So no matter where you are or where we are, we can always watch the operation of the system because the logs are streamed through MQTT. We're thinking about Amazon SNS. And so you can observe, whole teams can observe the operation of their algorithms because the logs are sent out. You don't have to actually have access. You just log into the web page. So that's it. And I have this quick thingy here. I don't think it's a link. We'll see if it will actually go. And this is the parallelization piece. So this is our distribution end. Can I make a new? Yep. Okay. So this is the end that we distribute from. And there's a couple things, if it comes, oh, it's a good day today. Amazon is up. The first thing you notice is the IP address. It's NASA policy. You can't use, you can't attach a NASA name to an Amazon address for the Amazon system we have. There are exceptions, and we would like to be part of that. So we'll look at the one that Louis was talking about. This is our RAIN capture, and this was done a long time ago. And so this is what I was talking about in the optimization. You can see the this is the whole pass is these green, the area covered in green. But each granule, what we'd like to do in the future is process those in parallel. And so we'd start multiple containers that would each process the one in order to get the higher time. And this really affects the flood algorithm, not so much the fire. Fire is like lightning. The flood algorithm would process this all as one. And so you can get times of up to 30 minutes doing the CSPP flood algorithm if it has to process that much data. So we're looking for increases in speed or decreases in speed by just reducing the amount that there is. So, and we also distribute the files are there for people to pick up and everything. So we could take a look at what came out of there, I think. Yeah, so we just make thumbnails and then people, this is really designed for automated pickup. And it's on EFS rather than S3 only because we haven't converted yet. So I'm sorry, over time I'm delaying us getting to lunch. I thought with 10 slides I'd be done in 10 minutes. Any questions? And thank you very much again.
Okay, so I see we do have a question from Liam.
Thank you very much. That is really fascinating stuff.
Sorry if I
So
overloaded.
the cross-region data delivery, you said it delivers 30-second chunks of
Yes.
something. What are those chunks exactly?
So what was mentioned earlier was they call it a PCAP file, and what it is, correct me if I'm wrong, it's the signal from the antenna past are you familiar with Data Defender?
A little bit.
It's just past the Data Defender stack. And so it's received in station, piped through Data Defender, so I guess it's a data cleaning. And then they send you what would come out of Data Defender. So it's no longer a sound file or music file format. It's actually got data and structure to it. And so it's got the Vita49 in it, which you need to strip off. And I didn't mention earlier that Amazon team distributed an application, which now looks like is in the function. We had to reverse engineer the code and recode it into a new format because it was done over the sockets, so the local host socket. And so with that PCAP file, the good thing about the PCAP file is you can aggregate maybe 2 or 3 minutes worth of PCAPs and then start processing that right away.
So I guess my question is it the format that you would feed directly into RTS-TPS?
No,
It's
you
not.
got to remove the Vita49
Okay.
and aggregate as well because you get 30 different chunks. So in addition to aggregating them, you've got to strip the Vita49.
Okay. Thank you.
Okay, thank you. Oh, okay, one quick question.
So I know we talked a little bit about the timeliness of the flood algorithm.
Yes.
So right now it is not, does not contain an option to use CPS and CPUs as you like. But I think that is a request that you would like to see in the next version.
Well, we are debating. So with our funding, we're going to parallelize it ourselves, or if we did that segmenting, and I think it was in the Amazon talk as well, you have to re-put all the NetCDF files back together. And so we're kind of on the fence about which way to go there with the time that we have.
We should talk more about that.
Awesome.